All right, good morning. Let's get started here. I'm excited for our annual 3-minute thesis competition. We are doing this now for a couple of years, and it's always been an exciting event to hear from our graduate students in simple terms what they're researching and what the impact of their research is.
Okay, good morning, everyone. I want to know how many of you like trees? Thank you very much. So like many of you, I also have deep appreciation for trees. Trees carry hopes and emotional values because they often outlast human lives. But as engineers, we also rely on trees' resilience to help us adapt to climate change, like reducing storm water runoff or cooling streets. However, urban trees are also facing the same climate crisis that we are asking them to fix, along with urban-specific stressors such as poor soil and invasive species. So how do trees and green infrastructure interact with built environments? My PhD research investigates this relationship at 3 spatial scales. At a tree scale, since 2022, I have been monitoring 18 ash trees in the city of St. Paul using a compact and low-cost sensing system that I have built and designed to measure their water uptake. Despite treatment for emerald ash borers, these trees showed varying health levels, which affected their cooling abilities and also their runoff reducing abilities. Healthier trees cool more streets. But if you walk into any park, you may notice that some parks are cooler than the others. How may we explain this beyond tree health? I'm developing a model that explains how trees can cool surfaces through shade and water uptake, similar to how sweating can cool us. Paved surfaces dehydrate trees by limiting their water access, making it harder to sweat. Yet the tree canopy can cool these trees significantly. This leads to a dilemma where although trees are needed most in highly impervious areas, they struggle to thrive there. So going back to larger scale, I model green infrastructure's impact on flood reduction across stormwater networks under different rainfall scenarios. And my findings reveal that trade-off exists when you're managing different hydrological outcomes, such as upstream flooding or downstream flooding, and that green infrastructure benefits plateau and extreme storms. So for the civil engineers here, we have to ask, are urban trees meeting our needs or are they overburdened by our expectations? We must prioritize the health and maintenance of green infrastructure under the existing context of physical infrastructure. Oh, and I hope without care, trees can continue to carry our stories and hopes forward in face of climate change. Thank you.
When most people think of flooding, they picture a river rising or storm surges in hurricanes. However, in Minnesota, the state DNR estimates that 50% of flood damages occur outside of floodplains. This is due to very large storm events causing things like flash floods. Engineers in particular are concerned about these large storm events, often using hypothetical design storms, like the 10-year storm, a storm that we expect to occur about once every 10 years. And unfortunately, those of you that avidly watch the Weather Channel know, it feels like these really large storms are becoming more and more frequent, a lot more often than 10 years in between. So my research is examining how these extreme precipitation events are changing, and particularly with regards to climate change. But how do you study something that only happens once every 10 years? If you have a century of weather data, you might only have 10 data points. So what my research does is take a very large number of stations, 1,251 to be exact, and looks at the occurrence of these large events. We sorted each station to analyze when their 10th percentile events occurred, and then tracked what years did these total stations have an average occurrence level. And that generated the plot on the right. The dashed line is what we would expect in a stationary climate, about 10% of stations seeing a 10th percentile event every year. However, the data diverges from this assumption. In the modern period, we're about 50% more likely to see such an event, which is a large increase. This research has a few implications. First, it gives us something more than just this gut feeling from watching the Weather Channel. It shows that we can run statistical tests on this model and get a value of about 0.000005. That this is increasing. Climate change is real. Woo. So that's step one. Taking research like this is also important for informing stormwater managers and engineers about what future storms might look like, so we can prepare not just for what exists today, but what is coming down the stormwater pipeline. Additionally, this allows us to check global climate models or theoretical models that model atmospheric currents and say, do they match historical data? And if they don't, then perhaps it's time to rework those to better reproduce what we know has actually occurred and project further into the future.